Good morning, afternoon, or evening to folks tuning in from around the world. As is tradition, why don't you let us know where you're tuning in from? Welcome to the 170th episode of the Qiskit Quantum Seminar. And just a reminder, this seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. You can always subscribe to go back and catch up on anything you missed. We can only ask questions here, live now, during the seminar. I'm Derek Wong, a research scientist at IBM Quantum, and I'll be your host today. Of course, there's a lot of care and effort that goes into these seminars, so I'd also like to thank video producer Paul Searle, managing producer Olivia Lanes, our producer and host Lako Minev, and co-hosts Ed Chen, Katie McCormick, and Nick Braun. So yeah, welcome John, Mitch, W, Jeffrey Berger, NYC represent Javier. Today we'll be hearing a talk by Javier, who will speak about chemistry beyond exact solutions of the Schrodinger equation on a quantum-centric supercomputer. Javier is a research scientist at IBM. His research focuses on the use of quantum computers and machine learning techniques to simulate quantum many-body systems, and in particular, electronic structure problems. He obtained his PhD in physics from NYU in 2023, where he developed machine learning techniques to tackle the quantum many-body problem. Prior to that, he obtained his BS in physics from the UAM in 2017. Take it away, Javier.
Thank you very much, Derek. It is my pleasure to be giving this talk today. As you've mentioned, I'm going to be talking about our newest results on the simulations of molecular systems using quantum-centric supercomputing. This has been a large collaboration between IBM Quantum, RIKEN in Japan, and the University of Colorado Boulder. And then it's been, a great effort from a great team of people. So so let me begin with the talk. So to give you a little bit of motivation of why we are using this type of techniques to tackle electronic structure problems, I would like to begin with some back of the envelope estimations. The current belief is that pre-fault-tolerant quantum computers in isolation cannot deal with realistic formulations of nature. And to motivate this statement, let me, again, run some back-of-the-envelope estimations. Let's say that we want to find, for example, the ground state of this iron-sulfur cluster, which we are calling Fe4S4. If we map it through Jordan-Wigner into our quantum devices, it would correspond to 72 qubits. And just to measure the expectation value of the Hamiltonian for this molecule, I need to measure the expectation value of 6.7 million Pauli operators. Now, if I want to obtain chemical precision just on the expectation value of this Hamiltonian, because of accumulations of errors, it means that I need to obtain 10 to the minus 10 precision on each Pauli operator. Because of central limit theorem, this means that I need to execute each of these circuits 10 to the 20 times. And assuming a typical runtime of 10 microseconds per circuit, it means that you're going to be measuring expectation values for just 3 million years, right? So we need to improve this runtime somehow. So the point of this work is that we show that classical distributed computing enables quantum to address complex use cases with a few large quantum circuits. So what we're going to be doing here is we're going to allow quantum do what it does best, which is execute a few very large quantum circuits, and then let's allow classical to do the post-processing of the quantum data. I would like to begin by highlighting the results that we have obtained with these types of approaches, and then I will describe in more detail how the workflow that we used works, and then I will go back into describing in more details the results. We studied the bond breaking of the nitrogen molecule, which is, again, it's typically a fairly challenging bond breaking to describe because of strong correlations. And we showed that with this type of approaches, we were able to qualitatively correctly describe this bond breaking on a correlation consistent basis set for the first time. This is a 56 qubit experiment. So yeah, we're very excited about these results. Then After describing this bond breaking of nitrogen, we moved into trying to describe the ground state properties of more complicated molecular systems, and in particular, iron-sulfur clusters. Iron-sulfur clusters because, again, they are hallmark of a strong correlation, which comes from complicated magnetic orderings in their ground states. The smaller iron-sulfur cluster that we studied is Fe2S2, and here, through an energy variance analysis, which we will describe in more details later, we show that for the that we can discover multiple eigenstates which are very close in energy. And like this showcases that there is a strong correlation in this system. We show that through a linear extrapolation in this energy variance plane, we can obtain good agreement with the state-of-the-art classical methods, including classical selected configuration interaction and DMRG. This is a 46-qubit experiment. Now, we wanted to push both quantum and classical hardware to test the boundaries of these types of workflows, in today's devices. And we went into an even bigger iron-sulfur cluster, Fe4S4. Fe4S4 is, well, first of all, its ground state is even more complex than the Fe2S2 iron-sulfur cluster. And also, it's a bigger molecule, so you need to use more qubits. In this case, the experiment was a 77-qubit experiment. And again, we perform an energy variance analysis. And the point of this experiment was not to show great agreement with classical methods. Again, it's a very challenging experiment. It is mostly to just showcase that we can extract a useful signal from our quantum devices. And again, I will describe all of these results more in detail later in this presentation. Okay, so what is the recipe that goes into being able to obtain these results on molecular systems? Well, the recipe has two ingredients. The first ingredient is a quantum estimator that uses massive amounts of classical computing to process individual quantum samples. And the second ingredient of the recipe is a class of quantum circuits of tunable depth and therefore accuracy for the accurate preparation of molecular ground states. So these are the two components that I'm going to be describing next. So what goes into the HPC quantum estimator? Well, first, let me begin with some properties and highlights. This HPC quantum estimator allows us to handle observables with millions of Pauli operators, which is the typical size of the observables that we need to take into account for chemistry problems. It gives no false positives for ground states, so estimations of energies are always upper bounds, or it satisfies the variational principle. So then you can rank the quality of your results by saying, okay, who has the lowest energy? It relies on massive distributed classical computations. As for any near-term type of experiment, the complete removal of the effect of quantum noise comes with an exponential runtime in the noise rate. And also its performance is guaranteed for concentrated or sparse ground state wave functions. Okay, so what is this HPC quantum estimator? What is this quantum classical workflow? Well, we begin by preparing a quantum circuit here labeled by psi in the quantum device. And what we're going to do is, instead of extracting expectation values directly from the quantum device, we're just going to sample. We're going to sample in one basis. This is going to give us a collection of bit strings. What these bit strings represent, they represent electronic configurations. So they represent occupancies of orbitals given by the electrons. Okay, so if I have a bit string that is, for example, 1100, it means that the two first orbitals are occupied and the second two are empty. Now we pass this set of measured bit strings or electronic configurations into the classical side of the workflow. Okay. And the first thing that goes into this, the classical side of the workflow, is something that we're calling configuration recovery. Chemistry problems have a very important property, which is that they preserve the number of electrons. Since the number of electrons is preserved, we can very easily identify the bit strings that we have sampled here that definitely are corrupted by noise. And it's simply by looking at their Hamming weight. Bit strings with the wrong Hamming weight definitely have been corrupted by noise. So we're going to go through a procedure in which we define a probabilistic model, which is informed by the ground state properties of the system itself, to flip some of those bits to recover the correct number of electrons in those corrupted bit strings. Then the set of refined bit strings goes through a subsampling procedure. Essentially, we're just bootstrapping the distribution that we obtain. And the different batches of the bit strings are sent to separate eigenstate solvers, which are run in parallel. So now what goes into the eigenstate solver? Well, the eigenstate solver uses a selected CI solver, essentially. And the idea of using quantum samples to define these subspaces first introduced in this paper here. But essentially what we do is that given the electronic configurations that we have sampled, we project the Hamiltonian into the subspace defined by those electronic configurations, which can be done efficiently on a classical computer. And then we diagonalize the subspace, the Hamiltonian in the subspace, and this gives us an approximation to the ground state. Now, after all of these eigenstate solvers have been run in parallel, we collect the results, and these results are actually fed back into the configuration recovery module of this workflow to better inform the bit flipping procedure. So in the very first iteration, the configuration recovery module is not going to be a very good job because it doesn't have a very good estimation of what the ground state properties should look like. But as we keep refining and refining the bit strings, then this ground state, the estimation of these ground state properties that we use for the bit flipping are going to get better and better, and therefore the configuration recovery is going to get better and better. Okay, so also, I would like to highlight something about this type of workflow, and is that, opposite to typical quantum classical workflows where the information transfer between quantum and classical is extremely limited, here we have a lot more information transfer from quantum to classical. Usually, from classical to quantum, we pass circuit parameters, and from quantum to classical, we just receive expectation values. But those expectation values are also obtained as averages of samples. So what we do here is, instead of just saying, just combine the samples in a very restrictive way and give me the results, actually just pass me all of the raw data, pass me all of the samples, and I'll use those samples in the most expressive possible way to find an accurate representation to the ground state of the problem that I am interested in. The diagonalization procedure that we are doing here has a very interesting property, and is that it's somewhat noise tolerant. And I'm going to give an example of how it's somewhat noise tolerant. Let's say that we have a 4-qubit example and that we have 2 electrons in our system. So our bit strings are going to have 2 zeros and 2 ones. Let's say that the ground truth, the true ground state in this case, which I'm just, defining arbitrarily, this is a completely contrived example, is the linear combination of these 2 bit strings, occupied, occupied, empty, empty, and empty, empty, occupied, occupied. Now, let's say that because of noise, I sample 1 bit string, which is not needed to describe this ground state, which in this case, it would be a 1, 0, 1, 0. I'm going to project the Hamiltonian into the subspace of these 3 electronic configurations. So this is a 3x3 matrix, and I'm going to diagonalize it. Well, the diagonalization procedure is going to tell me that the bit string A and bit string C should have non-zero amplitudes, whereas bit string B should have 0 amplitude. It does not intervene in the description of this ground state. So even though it was introduced because of noise, then the diagonalization procedure is just going to ignore it. It's going to remove it automatically. But now the question is, can we do better than just letting the diagonalization handle the effects of noise? This is where we introduce this configuration recovery heuristic. And the configuration recovery heuristic again, it relies on being able to identify electronic configurations which have certainly been corrupted by noise, and those are the ones that have the wrong Hamming weight. So coming back to our simple 4-qubit example, let's say that I receive an electronic configuration that only has a single one. I know that I need to flip one of these zeros back to 1. And the nice thing is that I can use some information about the physics of the problem to perform this bit flipping. And in particular, the information that we are going to be using is the average orbital occupancy defined as the overlap, as the expectation value of the number operator given the ground state, okay? Great, so if I know that the average orbital occupancies are high, then this is giving me information. This is telling me that I should flip this bit with high probability, whereas if the average orbital occupancies are low, this is telling me that I should flip this bit with very low probability. So we're defining a probabilistic model to do this bit flipping informed by these average orbital occupancies. And then we just sample one of these possible bit flips and include this electronic configuration back in the pool of electronic configurations that are going to be used to perform this subspace expansion and diagonalization. Okay, but now here one question that can come up is, okay, but where do I obtain my average orbital occupancies, right? It's an expectation value that depends on the ground state itself. Like, do you assume that you know it from a classical approximate method, or how do you compute it? Well, we actually don't assume that we know it a priori, but instead we compute it and refine it self-consistently. So in the very first self-consistent iteration, what we're going to do is we're going to ignore the electronic configurations that come with the wrong particle number. This is doing post-selection, naive post-selection. We run the whole workflow. This is going to give us a first guess for the average orbital occupancies. This first guess is most likely not going to be very good, but nonetheless, we're going to use it. We're going to go back to bring back those configurations that came with the wrong Hamming weight. And after doing that, we are again going to run the eigenstate solver, recompute these average orbital occupancies, which they're going to be refined, go back to configuration recovery, and look again at the bit strings that came with the wrong particle number, and refine them again, and so on. So this is how this workflow is working. Now,
maybe
yes,
time where I could ask a few
yeah,
questions
yeah,
from
absolutely.
the audience. One question that's come up is this variational bound you mentioned in the very beginning. Does that hold in the presence of noise? I guess, like in my head, I'm thinking of two kinds. Like coherent noise, it seems like it would not really obey this variational bound, and the second is sampling noise.
So this is a really good question, actually. The nice thing about this type of quantum classical workflow is that variational bound is always guaranteed. And this is because what is giving us the estimation of the ground state energy is a classical representation of the wave function. And this classical representation of the wave function is it preserves the norm. So yeah, it's.
I see. So somehow doing this projection to this classical wave function will guarantee this.
Yeah,
regardless of the state that it came from originally.
Exactly.
I see. Also to the audience, if you see us looking at each other, it's because we're sitting right next to each other in the office right now. Okay, so then another question I have is related to sampling noise. So at some point, you have to diagonalize within the subspace of bit strings you've sampled from. So, on a laptop, let's say at best you can diagonalize like 10,000 by 10,000-ish. That means you can only sample at most like 10,000 unique bit strings. And we know sampling noise goes as like 1 over the square root of the number of shots. And so somehow that seems to me like this diagonalization step is limiting your precision to, order 1% of energy. Maybe that's a little bit too convoluted, but overall, I wonder, like, how many shots do you actually sample in practice, and does this sampling cost limit your precision of the final energy?
Yes, so this is a very good question, and it's also a complicated question to answer. Let's say if the distribution that we are sampling from is the perfect distribution, And if the ground state is also concentrated, this is if the distribution that we sample from shares the exact same support as the ground state and the ground state is concentrated, then this should not have any statistical uncertainty. Okay, if there's no noise and we're all in perfect conditions. Now, when that is not the case, you are absolutely right. There is a statistical uncertainty. There's also a statistical uncertainty when we do this bootstrapping procedure as well. We do observe in practice that, of course, the more samples that you compute, that you get from the quantum device, the better your results become. I think that in the future, we definitely want to study the statistical convergence of these estimates of the energy more carefully.
I see. Okay. Yeah. And I guess this relates to this final question I had more broadly is there a way to relate the error you get if you were to measure the energy of the sampled state, if you can relate that error to the final error you get in this hybrid quantum classical energy you
Okay.
get?
So what I understand you are asking is, okay, instead of giving an estimation of the energy from this subspace diagonalization, let's look at the energy of the state that produced the samples itself. So actually what we observe in practice is that the energy that produces the samples is significantly worse than the energy that you obtain here. And there is a very good explanation for that. And is that all that this state needs to describe accurately is the support of the wave function. It doesn't need to describe very well either the wave function amplitudes or the signs. So you can completely lose all of the information about the signs of the ground state and still produce an accurate representation of the ground state itself using this procedure.
Okay.
And this also speaks to something quite interesting, which is that if you were to try to optimize the circuits, you can use the variational power of the parameters not to, for example, catch complicated sign structures, but to get the support correctly. So to some extent, it has a little bit more variational freedom as compared to just targeting the ground state energy.
I see. Great. Thank you.
Okay. So now speaking of circuits, what goes into the circuits, right? Oh, actually, I'm sorry. Before going into the circuits, I want to show you some numerical results on the effect of adding configuration recovery. So this is a numerical experiment where we say, okay, we're going to inject noise by hand. So we have a probability of measuring some electronic configurations, noisy, which is modeled as alpha, the noiseless distribution, plus 1 minus alpha, just completely white noise. Here, alpha is a parameter that we can tune. In our simulations, alpha equals 1 means that we only have signal. Alpha equals 0 means that we only have noise. And we're going to run these numerics on the dissociation of, again, the nitrogen molecule in a Popol basis set. This would be a 32-qubit experiment. And here what we show is the energy error in the ground state, average over 24 bond lengths, and as a function of alpha, as a function of the amount of signal that we have. So from alpha going from 1 to 0, what we see is that if we just do post-selection, the error grows fairly quickly. If we include this configuration recovery procedure, the error grows significantly slower in this case. And in particular, what we notice is that if we want energy errors below 10 millihartz, again, completely arbitrary threshold of accuracy set here. If we just do post-selection, we need 20% of signal, whereas if we include this configuration recovery, we only need 2% signal to obtain an equivalent amount of accuracy. So this is configuration recovery here is helping us a lot to extract useful signal from our quantum devices. Okay, now what goes into the quantum circuits? Well, we are using these local unitary coupled Jastrow circuits, which were pioneered by some of the people in the group of collaborators. So when it comes to designing quantum circuits for electronic structure, we have two families of circuits. We had either the hardware efficient or the physically motivated quantum circuits. The hardware efficient are very compatible with hardware. They require fairly low connectivity, very low number of gates, very low depth as well. However, they are very hard to initialize and also to optimize. On the other hand, we have the physically motivated, for example, unitary coupled cluster with singles and doubles. They have some very nice features, such as that, their parameters can be obtained from classical calculations. They are much easier to optimize. However, they require typically all-to-all connectivity in the quantum device and also high circuit depth and gate count. So this local unitary cluster Jastrow circuit tries to find a middle ground in between these two families of circuits. It borrows physical motivation from coupled cluster theory, and it also tries to obtain some hardware friendliness by performing some approximations to have devices to end up with a device-specific connectivity. So the starting point of the circuits, as I mentioned before, is a unitary coupled cluster singles and doubles circuit. Here, where the cluster operator only contains single and two particle excitations. We can perform the composition of the cluster operator into the linear combinations of diagonal density-density interaction terms, density-density in between all possible pairs of qubits, sandwiched between orbital rotations. This is a standard factorization of this cluster operator that can be done. Now, the approximation comes from truncating some of these coefficients J that tell us what qubits should talk to each other to just allow connections between physically adjacent qubits in the quantum device. So what we end up with is a circuit that is composed by several layers of orbital rotation circuits, sandwiching this time evolution of density-density type of interactions. These circuits have some nice properties. Again, similar to unitary coupled cluster with singles and doubles, the circuit parameters can take as an input parameters from classical calculations of coupled cluster or configuration interaction type. This is what we have done in our experiments, by the way. The circuit parameters are obtained from coupled cluster singles and doubles. There is evidence that they can perform better than their classical counterpart. We know that in some limits, these circuits, we don't know how to efficiently simulate them classically. And they are also compatible with hardware. The implementation of these orbital rotations require one to just apply two qubit gates in between physically adjacent qubits. As I mentioned before, this time evolution of density-density interactions, we are just truncating them to, again, only be applied in between physically adjacent qubits. This is an example of one of these circuits. This is one of the circuits that we have used for one of the nitrogen experiments. As you can see, the circuits are, getting to a very large size. In particular, it contains 1700 C nodes. For Fe4S4, we went up to 3,500 C node gates. And still we were able to extract a useful signal from the quantum device.
Javier, I have a quick question. So it seems like the way you get this local unitary coupled Jastrow from the full unitary coupled Jastrow is just to drop terms that don't abide your connectivity.
Yes.
Why couldn't you do that from the standard unitary coupled cluster ansatz and just drop connections that don't work well with your connectivity? Is there something special about the fact that in this Jastrow basis that makes this dropping of non-local terms better controlled?
So that's a really good question, actually. I think that it's a little bit better controlled because you start from the factorization of the cluster operator in terms of things that you know are going to be more local than the cluster operator itself. So it's a little bit more controlled in that sense. Yes.
I see. Okay. It's like the basis you start from is more amenable to this kind of.
Exactly.
Okay.
Exactly.
Thank you.
All right. These are some circuit layouts that we have used for our experiments. Again, nitrogen 58 qubits, Fe2S2 45 qubits, Fe4S4 77 qubits. The red qubits correspond to spin-up orbitals, the blue qubits spin-down orbitals, and these green orbitals are auxiliary qubits that are used to have density interactions between opposite spin species. Okay, so now let's discuss the results that we have obtained. Again, let's go back into the dissociation of nitrogen in a correlation consistent basis set, double zeta basis set. As I mentioned before, 58 qubit experiment. Here what we show is the energy as a function of the bond length for different classical methods for reference. So this is heat bath configuration interaction. This is the classical counterpart to this type of workflow. And then other classical approximation methods. And in brown, we have the dissociation curve obtained from our quantum experiments, which again, it qualitatively is in very good agreement with what is expected from the dissociation of this molecule. It's typically, we chose this, the dissociation of nitrogen because the triple bond breaking of nitrogen is recognized as a test bed for accuracy of electronic structure methods. Because again, it's fairly statically strongly correlated. Then we moved into the study of these iron-sulfur clusters. And again, iron-sulfur clusters, they are also a hallmark of a strong correlation, which comes from complicated magnetic orderings of the electrons in their atoms. We begin by this Fe2S2 molecule. This is a 45 qubit experiment. And what we did here, we did an energy variance analysis. So what is this? We know that if we're close enough to an eigen, so also something that I forgot to mention earlier is that we have a knob to turn the accuracy of this method, which is the size of the subspace where we project and diagonalize the Hamiltonian. The bigger that subspace, the more accurate the representation of the ground state is going to be. Now, we also know that if we are close enough to an eigenstate and we increase the accuracy of our methods, the energy and the Hamiltonian variance, they are going to be linearly related. This comes from a perturbation theory argument. Now, what we see in this plot here, D in the color bar is the dimension of the subspace. So again, flowing from light yellow to dark blue, we're just increasing the accuracy of the method. If we run classical heat bath configuration interaction, what we see is that as we increase D, the method catches 3 different eigenstates, which are very close in energy. If we play the exact same game with our configuration recovery workflow, with the data coming from our quantum devices, we actually observe the exact same behavior. We also catch 3 different eigenstates very close in energy, and eigenstate C is what we think is, which we can identify as the ground state. And the extrapolation of the data from the quantum device is actually in very good agreement with the DMRG results, the state-of-the-art DMRG results, and with the very best point coming from heat bath configuration interaction. Also, something to note in these types of energy variance plots is that, again, the lower the energy, the better the accuracy of the result is, okay? So we were also very excited about this result because it shows that within this type of workflow, we can start performing, precise many-body physics experiments with our quantum devices, and again, in challenging molecular species. And lastly, again, like what we wanted to do with this experiment, we really wanted to push the limits of both quantum and classical devices. So again, we accomplished this by moving into a molecule that is bigger and that whose ground state is also more complex. And this is this Fe4S4 iron sulfur cluster, which is shown here in this diagram. This is a 77 qubit experiment with a total of 10,000 quantum gates and 3,500 2-qubit gates. Here we also show an energy variance type of analysis. But what we wanted to get out of this experiment is whether we could extract a useful signal, and to assess whether we were extracting a useful signal above just white noise. What we did is we ran our workflow both on quantum data and on just bit strings for electronic configuration sample from the uniform distribution. Those electronic configurations sampled from the uniform distribution are shown by the pentagons. Again, different colors correspond to different increasing subspace dimensions. And what we see here is that, okay, the pentagons are up here in the energy variance plane, and they are also not aligned whatsoever. Definitely not close to an eigenstate at all. From the quantum data, all of the points are down here. So again, remember, lower energy means better results. So indeed, we can show that we are extracting a useful signal from the quantum devices. And if we zoom in into this small section of the energy variance plane, we can also see that the points from the quantum device, they're also aligned. They don't match with the classical methods, but again, the point of this experiment is to show that we can extract a useful signal from our quantum devices. Also, something that we want to point out is that more classical computing allows one to extract better signal out of noisy quantum data. So I would like to end the presentation with a couple of main takeaways. The first one is that we have seen that quantum-centric supercomputing enables realistic applications of our quantum processors beyond problems specifically tailored to the devices. So now we can start dealing with more realistic descriptions of nature. We don't have to be limited to, for example, lattice models. Lattice models are extremely interesting, but what we see here is that we can start dealing with more ab initio type of problems. We see chemistry as a first example, where what we are doing is classical computing is processing big data coming from the quantum device, while the quantum device is just being used to execute a few but very large quantum circuits. And again, chemistry is just a first example. We hope to see applications of workflows of this type on other domains in the future. We were able to perform quantum simulations of molecules beyond the reach of brute force classical methods, and in particular this Fe4S4 molecule. Again, it's a 77 qubit experiment, so it's a very substantial experiment, and we showed that even having 3,500 2-qubit gates, we were able to extract a useful signal from the quantum device. By processing the quantum data at the individual sample level, we obtain an estimator that has no false positives, and this allows us to unequivocally rank different solutions, right? Lower energy means better, and this is great if one wants to get in the territory of starting to address whether one experiment has obtained quantum advantage, whether it has not, right? It's a game of seeing who obtains lower energies in less time and with less energy as well. And again, we are also very excited because we know that better devices and also increased classical computations will allow to obtain better results. So yeah, we are looking forward to to see what comes next. So with this, I would like to thank you very much for your attention, and I think now we will take some questions.
Yeah, thank you, Javier. Super interesting. And yeah, we have a lot of time for questions. So anyone in the audience, I see questions popping up already, but feel free to ask more over the next few minutes. I have some as well, and I'll mix in what the audience is asking too. So there are questions that are coming up about so what you do is you use the quantum computer to basically sample bit strings.
Hmm.
And so there are questions related to, well, can you use other classical methods to sample bit strings, like tensor network methods or some kind of Monte Carlo method? How would you compare those approaches to what you're doing here?
Yeah. So this is a really good question. There are indeed classical methods to sample bit strings, and again, like in the classical realm, this is called this goes under a very big umbrella term, which is called selected configuration interaction. And there are various schemes to perform the samplings on the spaces of bit strings. There are usually tree like searches where you start with the Hartree-Fock bit string, and then you keep expanding your space of bit strings and truncating and keeping those that remain useful to describe the ground state. Um, in particular, here heat path configuration interaction is a particular flavor of that type of
Mm,
scheme. Uh, in on Fe2S2, I think we obtain comparable results to in some cases to this heat path configuration interaction.
mhm.
Um, then sampling from tensor networks, this is a really interesting idea. Myself, I haven't seen any works along those lines, but I think it would be really interesting to see whether tensor networks can produce
Yeah.
accurate probability distributions.
Great, thank you. And I guess related to this is what you get at the end of the day is you get an energy estimate from this optimized uh, distribution of bit strings. But often in chemistry, getting the ground state energy is just the start, right? Because
Hmm.
often you're interested in having the state, and with the state, you can compare excited states to dynamics or compute other properties of the ground state. And so in your situation, with this optimized set of bit strings that gave you this nice energy, can you use those to do the same things you would do
Yeah,
otherwise? Okay.
yeah. That's again like a very good question. So once you have the bit strings and you have the estimate of the energy, you also have an estimate of the ground state wave function, which is just written as a linear combination of those bit strings weighted by the
Hmm.
coefficients which actually come out of the classical diagonalization. So whenever you get the energy, you also get an estimate of an approximation to the ground state wave function.
Yeah.
So yeah, like you can use this ground state wave function, as you mentioned, for example, as a starting point for maybe more, convoluted methods to maybe recover
Mm,
dynamical correlation, or as a starting point for excited state calculations or dynamics. So
hmm.
yeah.
I see. Cool. Um, so then there's another question here from Shabazz about whether your entire procedure at the end of the day like really gives you benefits in the presence of this quantum noise and decoherence from the device. My interpretation of this final slide you're showing here, or the one that's actually
Oh,
on the
yeah.
page right now, is that you get this useful signal, and so you're claiming that yes, overall, it is worth doing this on a quantum computer despite the noise. So maybe to extend their question, then, like, when do you expect the device to fail you?
Hmm. So the quantum device can fail in multiple ways. Let's put it this way. Um, there are so to, again, like let's assume that the ground state wave function is concentrated, and here what you're playing is a game of guessing the correct electronic configurations, the correct bit strings. Um, Here we are exemplifying one failure mode, which is you're just producing a uniform distribution over all of them. So it's when it's exponentially hard to distinguish what are the relevant bit strings in that scenario.
Hmm.
Another failing mode is where instead of giving you the correct ones, you have a very strange and very awful noise mechanism, which actually just spits out a concentrated distribution, but doesn't have the correct support.
Mm.
That could also be a failing mode where you have failed. Um, n- that's what I can say about it. Um, then again, the comparison against, I think this question might also be related to, okay, how does this compare to other classical search methods? There are some classical search methods that in worst case scenarios also need to explore an exponential amount of the Hilbert space before it finds the correct subset of bit strings. So again, like if you have a distribution that doesn't need to explore everything in those worst case scenarios, then this could be very beneficial.
I see.
So it's, let's say you can see the quantum device as another tool to produce these distributions on a space of electronic configurations.
Yeah, makes sense. Thank you. Just a couple more questions. One is you in this study, something I find interesting about it is that for a long time it's been about comparing classical methods versus quantum. And these quantum methods, typically, if there is any classical overhead, it's not very high, right? In many variational studies, for example, it's just a simple Hartree-Fock, and that's pretty low overhead. But in this case, a major cost is the use of the classical resources. And so then I think it's fair to also compare the classical resources used in this method against the classical resources of the pure classical methods, like the coupled cluster and the other methods you show. So do you have a sense for what those resource counts look like, what the scalability looks like?
Yeah. So again, this is a very good question. As of right now, to obtain comparing accuracies, yes, what we see from the quantum device is that it takes us more computational resources to obtain comparable levels of accuracy. Otherwise, the claims of this work would have been much bigger, right? But for example, on Fe2S2, is not that far away, the amount of classical resources that you need in some of these. So here what we are comparing is the crosses versus points, and a comparable amount of classical compute would be if the points have similar colors in this scale, and a comparable amount of accuracy would be if they are at the same level of energy. There are some points here which are not too far away. Again, we haven't seen individual cases where, oh yeah, you beat the classical runtimes. That's for sure not what we have seen yet. But I mean, that's something that we hope that we will see in the future.
Yeah, absolutely. Great. I'll leave it off with just one final question then. And this has come a lot actually from the chat, is what problem areas do you envision this method being directly applicable to in the near future?
Beyond chemistry,
Yeah,
I
beyond
assume.
chemistry even.
Okay. I mean, so a big domain of application again is electronic structure. Here we are dealing with molecular systems, but also we hope that we can start doing extended systems in the future with embedding techniques. So that's one particular application. We are also looking into, so in general, we think it's going to be quite useful for quantum simulation, and quantum simulation has, of course, multiple flavors, right? This is just ground state search, as you have mentioned before, Derek. We also have excited state search and preparation, right? This is also something that I think this type of approaches can be very useful for. Beyond excited states, then we also have time dynamics. Time dynamics in subspaces could also be quite interesting, although I'm not sure about the sparsity of the wave function, right? Here we rely on the fact that we expect the ground states to be sparse. When you do time evolution under arbitrary Hamiltonians, I'm not sure how that is the case, or whether that is the case, but yeah, I mean, I think that these are all open questions that are, hopefully we can address them in future studies.
Yeah, of course. Well, thank you so much for coming in, Javier. This was a very interesting presentation. And of course, a big thanks to the audience for tuning in. Today was especially active in the chat. If you'd like to continue the conversation, hop over to the Qiskit Slack workspace or talk in the comments of this video. So like this video, subscribe to the YouTube channel, and we'll see you next week. Thanks, everyone.
Thank you.